welcome everyone to day 2 of CANS. And Marcel Keller is a senior research scientist with CSIRO's Data 61, which is a business unit of Australia's National Science Agency. And well, he completed his PhD with Ivan Damgaard at Aarhus, and then he spent a few years at Bristol under the supervision of Nigel Smart. And what he's going to talk about is, well, his work that he started on under the supervision of Nigel Smart was the implementation of multi-party computation, and that would eventually form the basis of MP-SPDZ, which is the topic of this talk. And this project is an open source project used by researchers all over the world. And I'm happy to announce that Marcel Keller will give this talk on MP-SPDZ, a versatile framework for multi-party computation.
If there's no complaints, I'm going to start. I just want to say that what I'm going to say is my personal opinion and not the view of the CSIRO. Okay, so with that out of the way, let's talk about MPC. And for some of you, this will be new. For some of you, maybe not. But to kind of bring everybody up to the same level. So MPC is about protocols that compute on secret inputs. And like in terms of like, what can we expect from MPC is essentially we want to replace a trusted third party. So instead of giving all your information to someone you trust, for every participant, you want to run a protocol between these parties that eventually you come to the result that you want, but during the computation, no information about your secret inputs is leaked. And this has been around for a while, as you probably know, and there's many protocols, and these protocols like essentially differ along a few axes. On one hand, you have security aspects like how many honest parties among the parties. What do you expect from dishonest parties? Are they still expected to follow the protocol, or are they also allowed to deviate, and what happens then? And on the other hand, there is the more functional aspect of what is the mathematical domain you can compute in, because all protocols are essentially tied to a mathematical domain. And what do I mean by a mathematical domain? It's usually a modulus that you compute modulus, or be it a prime modulus or a power of 2. It's also possible to compute in more, say, exotic mathematical structures such as Galois fields of characteristic 2. And among all these possibilities, MP-SPDZ supports more than 30 protocols, and this looks roughly the follows. So per line, you will have security models, so security considerations like honest majority or dishonest majority, like which turns to be like a big difference in terms of what you can actually do. And then you have this subdivision into malicious, semi-honest, and the sort of in between covert setting. So semi-honest is a setting where corrupted parties are still expected to follow the protocol, and the malicious setting is the setting where this expectation isn't given. And then there's further, in that setting, there's generally further questions, you know, can you still come to a conclusion or not? In MP-SPDZ, generally, it's with a board. So if there is any deviation, it will be detected and the honest parties will abort. In terms of computation domain, we got the columns. So in the first column, we have like large fields, either modulo prime or fields of characteristic 2, and you will see there's like quite a lot of possibilities there due to the mathematical structure. If you downgrade, if you will, to a ring, which is a power of 2, you have fewer possibilities because it's sort of mathematically weaker, if you will. but it turns out that can often be faster because you don't have to do prime modular reduction. There's also a few protocols for sharing in F2, and that's just a different way of saying binary circuits. And last but not least, also with binary circuits, of course, you can do gobbled circuits, famous Yao gobbled circuits, and also various flavors of these so-called BMR constructions. But as you can see, the focus is firmly on secret sharing based protocols, and I would argue for many applications this is preferable simply because integer multiplication is a relatively straightforward operation in especially in like modulo 2 to the k and prime field domains. Okay, so well, it's all good and nice to have like lots of protocols in one framework, but why? Oh, I've got this slide. Sorry. So in terms of technologies, I mentioned secret sharing. In terms of underlying technologies, there's also homomorphic encryption and WBS transfer. I did mention gobbled circuits, and also a topic that has kind of become kind of more and more used is what I would call mixed circuits. So that's like when you combine arithmetic circuit computation. So that's like more modulo, a large integer, relatively large integer, versus binary circuits, which is modulo 2, both with secret sharing. And when you combine these two, it turns out you get efficiency gains because you can use the best of both worlds. So as I mentioned, in the arithmetic domain, modulo large integers, you get an integer-like multiplication, like relatively cheap, whereas of course in the binary setting, this is more amenable to say things like comparisons. Okay, and now I sort of want to make the argument that it really does make sense to have all the protocols in one framework because they share so many aspects. And for that, I want to talk a bit about this black box model, or in the papers you will find it by the name arithmetic black box. And it's essentially the idea that MPC gives you an abstraction of this black box that is held together by all the parties, and this black box contains values that the parties can input individually, secretly into the black box. And once in there, the parties know that this value is there, but they cannot access it directly. They can only cannot handle it via a handle, and if the parties agree that you want to add or multiply the values with two such handles, then a new value is created in the black box with a new handle. And after you've done that over and over and run over your computation, the parties eventually can agree to output any such value under a specific handle, either to one of the parties or to all of them. And the further unifying element is that in essentially all protocols, or at least all protocols that I would call practical, it almost entirely boils down to two basic operations, some addition operation and some multiplication operation. And in most efficient protocols, or all efficient protocols, I would argue, the addition can be done without communication, whereas you need communication for the multiplication. Think of Shamir secret sharing, if you know about it. Addition is just adding your shares, but for multiplication, you need to do some resharing to reduce the degree of your share. Similar in speeds or the related tiny OT, if you want to do an addition or XOR in TinyOT, you just add the shares and the max. However, for multiplication, you have to run this Beaver multiplication protocol that I will talk about later. And then similarly, in the world of cobbled circuits, there is this technique called free XOR that again gives you addition without actually having to gobble any gate, whereas for multiplication or AND, again, you actually need to do the gobbling. So this is a bit of a high-level overview and an argument that if you dissect the protocols a bit, they all kind of look similarly. So this gives the ground for having a framework combining all these protocols. And now to kind of for a moment to go a bit less abstract, I want to talk a bit about secret sharing just to get these people along who are not very steeped in the subject. So probably the simplest way of sharing a secret is just having a random sum. So if you want to secret share a secret X, you pick some random shares X1 and X2, and then you pick X3 such that the sum of all the shares of all the Xi's is your actual secret. And on this land, on the next couple of slides, I will use this black box at the bottom to symbolize the secret sharing. And of course, the linearity gives you addition and multiplication with a constant right away. So you can just add two sharings by adding the shares, and of course the sum is commutative, and it gives you a secret sharing of the sum. And very similarly, if you multiply every share with a particular value, you will get a sharing of the secret times set value. So this gives you like a very quick introduction into this addition is cheap or essentially for free idea that can be found in all of MPC. Now, of course, then once you have addition, the question is how to do multiplication. And one of these possible, one of the protocols, and one of the protocols that is widely used and also used by kind of several protocol variants in MP-SPDZ is this Beaver multiplication or Beaver randomization, Beaver triple technique, to name a few names that it's known by. And to set the stage, so you have X and Y sort of individually, like by an individual handle in the black box, and you want to have X times Y by a fresh handle. And how do you go about that? Well, you introduce two new values, A and B, and they're supposed to be fresh and random and secret. And you don't only want to have A and B in that black box, you also want to have the product of A and B in that black box. And this is the famous Beaver triple. And now, if you have that, which is a big if, and often it's quite involved to get this, and in speeds you use homomorphic encryption to get to these values. In further works like Mescat, you can also do it with oblivious transport. But once you have it, what you can do is you can add A to X and open it, and B and Y, and also open that. And this opening isn't an issue security-wise, because this essentially constitutes a one-time pad. Like if you remember that we're in a finite mathematical domain. And then once you've done all that, you actually can figure out that X times Y is a linear combination of the triple. And we have seen on the previous slide that the linear combination, like you can compute without communication. So what remains is that once you have a triple, you have a bit of communication, namely the revealing part of the mask and open, and then you figure out the rest without communication. So this is one multiplication. Now, of course, because in MPC, basically everything has to be broken down into these addition and multiplications, you are going to have a lot of these operations. So let's have a look what we can do when we just have two multiplications on the left side and on the left hand side and on the right hand side. And they're slightly different in that the second product on the left hand side uses Z, the output from the first multiplication, but on the right hand side that's not the case. So you can actually parallelize on the right hand side but not on the left hand side. And parallelize in this context of using Beaver multiplication or many other multiplications essentially means you can put the communication, you can batch the communication together. So you use only one round of communication instead of two rounds of communication, because we can do all the openings for all the multiplications in parallel. And in protocols, communication rounds are quite expensive, so that's something that you definitely want to do whenever possible. And this is where the first sort of the low-level interface of MP-SPDZ comes in, which operates at the C++ level, is that instead of sort of calling a function for a multiplication over and over, which of course in a library would just kind of go to another network call and another network call. You want to batch, or you want to use this batching. So the interface there is essentially initialization, prepare individual multiplications, then run the protocol, run the actual protocol all together, all the network communication in this call to exchange, and only that you get your results, your products out. And I would argue that this is the simplest possible way of doing this, while still making sure that you don't use more multiplication rounds than necessary. Now, of course, you can imagine that for a small computation that is easy to do manually, but imagine you want to do this, and I think none of you would like to translate this to all this for tuple round calls and figuring out everything out. So, and this is the sort of the very core optimization at the higher level in MP-SPDZ, where essentially we go from C++ to Python, because Python is kind of nicer anyway, and we have a compiler that essentially translates what you can see on the left-hand side, which is just easy, easy to write equations into this parallelized structure on the right-hand side. And that said, this is not exactly what happens. There is one more step that I will get to later, because we don't actually translate Python code to C++ code, but to a specific bytecode. But staying at the Python level for a moment, I want to give you a flavor how it is to program with MP-SPDZ and what it actually means like on the protocol level. So imagine you have a matrix and you want to we want to compute an array of the maximum of every row. Now on the left-hand side at the bottom, you find a straightforward Python code to do that. Just for every row, you go over all the columns and you figure out the maximum between the result you have so far and the next value in the row. Now, without any optimization whatsoever, the round complexity of the whole computation is essentially the number of elements in the matrix. Now, if you throw the optimization at it that I've already shown you, you will, of course, compute all the rows in parallel because all the rows are independent. So you, in a sense, if the matrix is square, you go down from squared complexity to linear complexity. But that's not the end, because in terms of rounds, that's actually not the optimal thing to do. You can actually go down to logarithm if you compute your the maximum of several values, kind of not going over the array or the row linearly, but actually if you compute a tree of maxima of all the elements in a row. And ta-da, actually, because that's such an important thing in MPC, MP-SPDZ allows you to do that with a simple function that's called tree reduce. And then goes you down to logarithmic complexity. So with a bit of MP-SPDZ magic, you go down from squared complexity to logarithmic complexity. And as an added bonus, if you do that with mixed circuit computation, so you actually use binary circuits for the comparisons that are of course implied by maximum, you will also come out at an optimal optimal bit packing at the low level, at the communication level. So I think this is really nice, and it sort of like demonstrates of sort of taking the global, the holistic view of putting things together in a modular way, rather than creating a sort of like, you know, one security model, one protocol, one application way of doing things. Okay, so after all this nice examples, we go to the overview of the tool chain. So as I briefly mentioned before, the compiler translates some Python high-level code into some bytecode that is specific to MP-SPDZ. And this bytecode then is executed by a virtual machine, and the virtual machine is programmed in this C++ interface that I showed you earlier. And for efficiency, there is actually one virtual machine per protocol, or more precisely, one virtual machine for like protocol combinations between arithmetic and binary circuits. And this allows for a really lean execution of the bytecode. On the Python level in the compiler, which is also implemented in Python, you not only have this optimization that I showed you, there's also a whole library that actually does this whole breaking down of high-level computation into the MPC low-level computation, which essentially consists of these additions and multiplications. So you can imagine there is like functionality like comparisons in there, division, and all sorts of mathematical functions like exponentiation and so on, sine, cosine. And of course, my main interest in terms of application over the last years has been machine learning. So there's a growing library to facilitate that, and I will talk about one result in the next section. So one thing that would be a good application of MP-SPDZ is privacy-preserving machine learning. In particular, in an outsourced training setting, that means you have on the symbolized by these hospitals, you have a number of data holders who have sensitive data. Think of health data, but they want to train a model on the combination of their data sets. But the data is too sensitive to just send it somewhere else, but they might be happy to secret share the data among a number of independent parties who then can run the training with MPC between them. And once they have done that, to either output the model back to the data holder so then can use it, or even continuously keeping the model and using it for inference in MPC again, so that again neither the input data to the inference is leaked to anyone in particular, and the model remains secret. And in particular, what I have done over the last year or so is I have implemented a concept of deep learning in MP-SPDZ. So what is deep learning? It's a sorry, I got a weird overlay on my screen. Deep learning is an established concept for so-called supervised machine learning, which means that you have known input-output combinations. So think you're interested in distinguishing cats and dogs. So you have a bunch of pictures of cats and you have a bunch of pictures of dogs, and you want to you want to create a model such that the computer from a picture by itself can say, well, this is a cat, this is a dog. What makes deep learning deep? So the deep in deep learning comes from the fact that we we fix the computation as a chain of functions, and these are called layers, and there's like no inherent limit to the number of functions other than resources, of course, and this is where the deep part comes in. Now, some of these functions have so-called parameters that change during training, and then this is what constitutes the learning. So we want to find the optimal set of parameters to get the best possible outputs from the inputs. And to facilitate the training process, essentially we add another function that's called the loss function, and this loss function quantifies the quality. So basically from a number of known input-output combinations and a set of parameters, we can compute a value that basically tells us the model is good, the parameters are good or not so good, or even worse. And that helps us because we then use differentiation to tell us how we have to change the parameters so that the model improves. And this is where the chaining of functions come in, because we can of course use the chain rule for differentiation and such that we minimize the loss, and this process is called backward propagation. And now to demonstrate the quality of our implementation. Oh, sorry, I'm surprised, continuously surprised by my own slides. A few words about building blocks. By far, the most important one is quantization, because floating point representation is very expensive in MPC, and thus MP-SPDZ. So it is usually done that we represent fractional numbers as integers, essentially just by shifting them a bit, and then we can use integer computation. Other than that, we need a bunch of mathematical functions like comparison, division, exponentiation, logarithm, and square root. All of it are implemented in MP-SPDZ to precision that comes quite close to how you compute on a CPU, and as we will see later, this helps with the accuracy a lot. So the takeaway here is the main deviation to computation as it's done classically really is the quantization, whereas the other building blocks are modeled very closely. So now we get to the dataset that we have used, and if you know anything about machine learning, you will not be surprised about this model. This has been called the hello world of machine learning, and it is a database of a few 10,000 handwritten digits by the American institution NIST, the National Institute for Standards and Technology. It's the inputs are 28 by 28 grayscale pictures, and of course the outputs, what we're going to figure out is a digit 0 to 9. And this is really important in the history of machine learning because it is the first to demonstrate the utility of so-called convolution, which is a linear function that kind of takes local groups of pixels into consideration. Because of course, when you think of anything graphical, it's very likely that pixels nearby have some sort of connection to each other, whereas pixels at completely different ends of a picture, much less so. So what have we found? Well, we have implemented the famous LeNet model, which is this neural network by LeCun et al. It uses convolution. It has 4 linear layers. So these are the layers with trainable parameters. We have used the AMS-Grad optimizer, which is a more sophisticated take on a stochastic gradient. And we have run the whole thing with 3 parties, one synchronous corruption on AWS, on the same AWS location, and we found we took 9 minutes for 1 epoch, so that is like 1 iteration over all the examples in the training database, and it took about 1 hour to reach 99% accuracy, and that's where the red line goes below 0.01 in the picture. If you compare it to clear text training, you can see we come relatively close, not quite there, and this is in line with earlier results that show that quantization does degrade accuracy either degrade accuracy or increase the error a bit. Okay, so how does that compare to another implementation that is out there? So we have compared our result with Cryp Ten. And Cryp Ten is a framework by Facebook that adds MPC functionality to PyTorch, which is a widely used Python-based machine learning framework. And what they do, they use less accurate approximations of non-linear functions. So think of approximating non-linear functions by polynomials. And we found that this has quite some impact even for MNIST, which is arguably relatively simple. So we would find that this often leads to divergence when you wouldn't expect it. So divergence is basically when your machine learning algorithm only produces garbage. So in the table you can see that our solution is more accurate than Cryp Ten's by like about 2%, which I would say is considerable given like how close we are to 100%. And then of course, on the other hand, because Cryp Ten is entirely implemented in Python, it also turns out to be a fair bit slower, whereas MP-SPDZ, as I said, uses C++ and has also been optimized over the years. Okay, so that's all I wanted to say about machine learning. If there are still no question, I will proceed to the last part, which is taking a step back and taking a bit more of a high-level overview on secure computation, if you will. And one thing about that is, like, now that I join like an organization that has some sort of practical perspective on things, I regularly get asked, well, what's good for MPC, what's good for secure computation, and what's bad? And I would say it's actually relatively simple. So basically good is when what you're doing is predictable, and what you're doing is what they call small input, small output. So for example, mathematical functions, one value input, one value output. That's not too hard to implement. There's plenty of that in MP-SPDZ. Think sine, cosine, division. Okay, that's two inputs, one input, one output, logarithm, exponentiation, and so on. And the other important aspect is that the computation path is predictable. And what do I mean by that? Think, for example, about the matrix multiplication. So if you multiply two matrices, you know ahead of time what you're going to do, like which value you're going to touch at which time. And this, of course, is perfect to implement it in an oblivious way. Whereas, on the other hand, think of graph algorithms. They are highly data dependent. You might be in a node and there might be no edge, or there might be some edges, and where do the edges go? So you have to go to a certain other edge, or do this, do that, and that is not predictable unless you know the graph, which in a graph algorithm is essentially your entire input. And similar to that would be like a dictionary data structure, for example, as a tree-based data structure. Again, you have this data-dependent walking down of the tree when you do excesses, and that's not particularly suitable for secure computation. And just before I conclude my talk with sort of air a few, let's call them opinions about the field. And the first one is that sometimes I'm surprised by how mystified people are by secure computation, and this is of course like fair enough. Like you have to learn about security models and what secret sharing really only to understand what's going on, but at the same time, I feel like the field has matured to an extent where there's so many building blocks out there, and unless you're what you want to compute, that is rather unsuitable for MPC, as I've said, like this, say, graph algorithms. Essentially, you can just take the building blocks out there and put them together and get the utility you want. Unless, of course, and this brings me to the second point, like everything is just too expensive for you. And I think that's, well, a tough act, because we know there are lower bounds, and I have a sense that we've come relatively close to these lower bounds. Like, never say never, there might always be like another great algorithm and scheme out there, but sometimes I get the impression that the people almost expect that there's going to be a lot of movement on the theory side to make things more efficient, and this is not something I'm very optimistic about. And then last but not least, this is like a shout out to the people who interact with me on GitHub or on other channels about MP speeds, and often I get questions or problems where I feel like I'm not being given enough information to comment on that. So I just would like to share, like, I'm always happy to help out, but you have to help me to help you, and kind of play with open cards, because otherwise we're not going to get anywhere. All right, and this is essentially what I have to say for today. Just to wrap up, there are a few links on the last slide. You can find MP speeds on GitHub, as I've mentioned. There is a quite extensive documentation. I think it's now like 120-130 pages or so as PDF on readthedocs.io. The paper that I published about MP speeds at last year's CCS is on my preprint. And last but not least, you can follow me on Twitter. Thank you very much.